So the cost of failure, got to know that, because that will be the reason that we want to make these changes. Not easy, because we've got this mindset and this culture we have to alter, but it's been done. That's how companies go from being dogs to being stars. They've changed their whole process. I mentioned before, one still in Australia. They've been doing it now for 8 years. You know, some companies take that long. If it's well entrenched and the bad practices are deeply entrenched, it takes time to make those changes. And hopefully 8 years is at the extreme end. I'd like to think that plant wellness might do it in 2 or 3 years. That's the thinking in my mind. To have a strategy where when we do these things, the right things are done and they're taught and picked up on quickly, because we can make the change quickly. So that's one of the things that Plant Wellness offers companies, is a rapid change to best practice, and not the 8 years that it can take if things are done haphazardly. This one here is, I guess, an enlightenment to me when it finally sank in. Only a few years ago. I'm 56 now. I was 49 when I began to say, well, this isn't working, let me look at some other answers. And it's taken me a number of years to get this clearer vision, I guess, of what we want to see happen. And this one here about series arrangements was one of the keys as to why we are so unsuccessful in changing to good practice at the moment. So I'm going to talk a little bit about reliability engineering and hopefully fairly simple concepts. This is a series system. A series literally is one thing after the other. So in this particular arrangement here of our pump, for this pump to pump liquid, the motor has to work, the coupling has to work, the pump has to work. I've got a system of equipment, so I've got a series, the whole three have to work. And of course, there's a base plate missing and a foundation missing and hold down bolts missing, so there's more to this system of a pump set to get the whole thing to work, but it's a series arrangement. Now, the chance of this whole system working depends upon the individual parts. This system requires at least these three to work. So the chance for the system to work is the chance of part 1 working, component 2 working, component 3 working, or assembly 1, assembly 2 and assembly 3. It depends how you want to look at this. I can break this down into components and it'll be the same concept, the same mathematics applies. Reliability, remember, is the chance of success. To have the system success very, very high, I've got to have every single component and assembly in the system even higher, because it's the chance of the whole system working as one that makes the system work completely. So I've put some numbers in there. Again, as an engineer, the numbers tend to clarify things for me. So here we've got a number of components. One component is 0.95 reliable, 0.95. Which means out of 100 times we go to use this thing, 5 times it doesn't last as long as it should do, 95 times it does. So I roll the dice and 5 times it fails and 95 times it's successful. So reliability is a measure we can get from the historical success or failure of an item of equipment. When I put 2 together, so I create a system of 2 now, so I need both to work as a pair for the thing to work. Now I'm down to 0.9 reliable. So my system of 2 is not 0.95, it's now 0.9. If I have 4 in a series, I'm 0.81. If I've got 10 in a series, I'm down to 0.6 reliability. Now this can be your production process, machine 1, machine 2, machine 3. It can be an assembly, component 1, component 2, component 3. It can be the parts, part 1, part 2, part 3, part 100 if need be. So I get to get, and this is how, so that the more I string together, the less and less reliable the system is, because any of these can fail. So yeah, very much like this, my domino. One item fails and the whole system stops. It's a big long chain, links in a chain. One link breaks, the chain fails. Same logic here. If that fails, doesn't matter, it's gone to zero. The whole system is unusable. Now with a system, there are some properties that are worth understanding. I'm going to work on this a little bit, so bear with me. Again, I'm going to use some maths just to highlight some of the issues out of this. There's 3 key properties that we work with in plant wellness. The first one is the reliability of a series system can be no higher than the least reliable component. Again, I'll throw some numbers up here. 0.9, 0.8, so R1, R2. Chance of failure. 90% chance of failure, of success, 80% chance of success. That's all it is. It's just the chance this might or might not happen. So my system reliability, our system, is those multiplied together. 9 eighths is 72, so my system reliability is 0.72, which is no higher than my worst. So if I've got a big lot of machinery in my process line, it says to me, if I want to improve my process results, I've got to find the worst performing machine and fix that machine. Because if I can push this up to 0.9, now I'm 0.81. Again, no higher than my worst, but I've improved the reliability. So when I do things like root cause analysis, when I look for a problem in my machines, I want to go to the worst machine, my top 10 machines, my top 10 worst machines, work on those to improve the business. Because it says very clearly, no point improving that one up to 1, perfect, when this one isn't touched. I'm going to work on the worst one. So in plant wellness, we're going to go looking for where the trouble is, the worst trouble, and solve that one first, because that is where the payback is for the whole system. Number 2 is if we add more items into a series system, say we've got a system of, we add one more to a system of 2 already, and each of those are 0.9 reliability. The reliability of all items must rise in equal proportion to maintain the system's original reliability. So if we have 0.9, and I add in another one, 0.9. My system, 81 minus 7, it's about 0.73. It was 0.81. It was 0.81. I've added one more thing in there, and as a system now, because all three have to work together, the system, of course, has reduced in reliability. If I want to get back to 0.81, I actually have to make all of these 0.93, 0.93, 0.93 to get back to 0.81. So I was at 0.81, I added something into the system, it dropped reliability. Now to get back to 0.81 where I wanted to be in the first place, I've got to lift all of these as well. So yes, I don't want to be adding things in. If I add things in, the chain gets longer with more links, and of course they're going to fail. And I think if I can go to the next, no, I haven't got that one there, wait a sec. No, haven't got that, that's okay. That's one of the slides I might add into this example. The third one is the one that's really, really interesting. What it says here, a small rise in reliability of all items. Say we're at 3 items at 0.93 and we go up to 0.95. We can lift each up to 0.95. The causes a much larger rise in system reliability. So let me just, now bear in mind I have no idea what causes this reliability to rise. Whatever it is that improves it is good to do. If we can do something, if we can go 0.95, 0.95, 0.95. If I can make that happen, increase reliability, then this one here goes to 0.86. This change is 2.2%. This change, I think, is 5%. Yeah. It says to me, hey, there's free money here. I put in 2.2% effort, I get 2.5 times return. Because I'm changing the entire system as one complete unit. And the mathematics is very clear. This isn't me making this up. The numbers are very clear. The proportionate rise at the individual component level is much less than the total delivery of the system. So the system improves a huge amount if I can create a global change. If I can create a global change across my company in one instant foul swoop, I will make absolute fortunes for very little effort. Question now becomes, what are the global changes that we can do that will do that sort of thing? Well, let's introduce precision maintenance. In the boardroom, the CEO's there with these execs, and we all say, guys, the company's now going to introduce precision maintenance. we saw before, if things are unstressed, if the stress is right down low at very low levels, we're going to create reliability. We're going to have far more cycles to failure than we had before. So the boardroom now does that, a global change. Let us introduce lubrication management. Every single gearbox, every single differential, every single hydraulic system, lubrication management. We're going to have world best lubrication management practices. Global change. Everybody gets trained up into proper lubrication management practices, good storage, no water contamination, removing wear particles, getting right down to very high quality conditions. So that decision across the years, every gearbox is protected, every hydraulic system is protected, every differential is protected, all by decision. So this is the stuff that plant wellness works with. I don't want to do individual spot changes. I want to make a business-wide change. And very simply, we bring in world best practice. Because we already know what it is. We've known for 25 years what world best practice is. I'm going to bring it in as a strategy. Things like precision maintenance, lubrication management. I'm going to upskill my guys. I'm going to have multi-skilled guys. I'm going to have guys that can do mechanical work and a variety of other work as well. So I'm going to have guys that understand their machines very, very well. My operators, I'm going to make them into guys that can do minor maintenance, do TPM from lean. Take the lean TPM concept, going to introduce TPM across the company. My operators are going to be trained up to become very skilled minor maintainers of machinery. So yeah, to me, huge money very, very fast. Not little henpecks here and henpecks there. Bring in best practice. Because it's already been done. The answers are already out there. Just bring them in, buy them in. And that tells me I'm going to make a lot of money fast. And that's what I'm saying in plant wellness, hopefully no more than 3 years, hopefully within 2 years. You're going to get far better results because this equation and the concept is very clear. Stop doing things that don't work. Do the things that do work. Teach your guys to do the things properly, correctly. Buy the machinery in, buy the instrumentation if you need to, because the payback is a fortune very, very fast. So yeah, that's something that didn't come to me until I was 52 years old, until I began building the course and began playing with what this plotting actually says. In a series process, we have huge risk. Because if that goes wrong, system fails. That goes wrong, system fails. That goes wrong. I've got hundreds of things to go wrong. And I want to have none of them go wrong. How do I ensure none of them go wrong? Bring in world best practice across the whole operation. Then I'm going to get the right things happening, and the right things happening give me the right results, and the right results give me a lot of money. Thank you very much. The other way we have reliability is to have things in parallel. So in a parallel system, here we go, we've got a standby unit. So what we do in parallel is we have standbys. So in this case here, that one can do the whole job. If that one fails, that one takes over. So I have a backup. And in many process plants, you'll have standby pumps and standby machinery on purpose, knowing that if one goes down, we start the other one and the process keeps on going. So somebody in the design phase thought about the concept of availability and the cost of downtime and said, no, I can justify putting in a standby because the risk is so great if we don't have it there. Now in this case, when I have a parallel arrangement, and again I throw some numbers in there because it's easier to see with some numbers. Here, 0.6 reliable. So one item is 0.6, and 0.6 is a disaster. 0.6 is absolutely atrocious. But I put 2 together, now I'm 0.84. I put 4 together, 0.97. I put 6 together, 0.996. So I can improve reliability by putting things in parallel. In the end, there's only 2 ways to improve reliability. One is to do things in parallel. The other way is to have each component very, very high reliability. And that's limiting, I guess, because there's not many things we can do to play with reliability. There's only a few options. Again, there's some things that come out of it in terms of basic implications. We use parallel activities or parallel arrangements when the consequence of failure is high. When the risk is high of one item failing, we put a standby in because it pays for itself. It reduces the chance of the process going down. We'd like to have things in parallel because it gives us options as to how to complete the process. You know, that machine goes down, that's okay. I can run it through this machine here. I can still stay in business even though I lose plant. The only hassle is that costs money. Now I've got to buy another one, maintain it, and keep it in good condition. So parallel arrangements, yes, reduce operating risk, but it adds on maintenance and cost and implications. But the payoff typically is there because there's a financial modelling done to justify installing these things. So yeah, we have the two choices, parallel activities, or we have a very high reliability of each component. Now what I've done here is I've taken the drive end bearing of an electric motor and turned it into what we call as a reliability block diagram. It's a process chain. I've said, okay, let's just take this section of the motor and say, okay, well, power comes through, there's a shaft journal involved, there's a shaft seal involved, there's a lock nut involved that keeps this thing working properly. If that lock nut comes off, we're going to have troubles with that shaft moving up and down. There's an inner race on our bearing. There's the lubrication, of course, between that inner race and the element. There's lubricant. We have a rolling element. In this case, it's a ball bearing. And again, we have lubricant on the ball bearing to the outer race. There's a housing bore. The housing's on the end cap's on the frame's on a base plate. You know, there's a whole chain here that I haven't actually put in there, but it's there. That might be, in the end, 50 components long. That fails. That goes down. This thing's driving my prize machine. This is the thing that drives the machine that makes money for the company. I'm out of production. If that goes down, same story. If that goes down, same story. So if I've got 100 of these things in line, any one of which goes down, my machine goes down, my process goes down, business goes down, I have to watch out what causes these things to fail. And that's why we focus so much on part reliability in plant wellness. I've got to make sure each of these really, really high reliability. Lots of nines in a row, because that is the only way to ensure this thing will survive 25 years trouble-free. So now I've got to say, well, what can destroy, if this fails, and I'm down and it costs me $2 million a day, I can afford to pay for some maintenance. So now I've got to say, well, how can my lubrication fail? And we go back to our table of the way things can fail. We can say, well, here are 15 ways to destroy the lubrication. Let's make sure that none of those happen in this company. Let's introduce the best practices to prevent that from happening. So these best practices pay back because lubricant is now safe and in great condition. My lock nuts never come loose because we put them on right and we double check they're right and you make sure the thing is correct. My shafts are always straight, always in alignment. There's no banana bending because they're got a soft foot problem. So that's the whole point of having a reliability block diagram. I want to draw our machines like this. I want to draw our business process like this, because any one of those fail, the business is in trouble. So I want to begin asking, what can cause my rolling element to fail? What can cause my housing board to fail? Well, if that's machined incorrectly on day one, manufacturer made it out of round, then I've got to start controlling my manufacturer's quality control too. Now, one other thing this does for us, this is actually the DNA of your machine. If you draw a reliability block diagram of your whole machine, that's a string of its individual genes. Each item's like a gene on our DNA. So if I can draw my machines out with arrangements like this, it's just a process flow diagram. That's what it's just I call it a reliability block diagram, but it's just a process flow diagram, boxes and arrows. So I can say, well, gee, wherever I see this string of arrangements in any machine in my business, then whatever works for this particular arrangement will work for that machine and this machine. So in plant wellness, what we do is we have a look at one bearing. How do we ensure one bearing is highly reliable for 25 or 30 years? And then whenever I see a bearing, I'm going to do the same thing again and again and again. So I don't analyse every single machine in the plant. I analyse the assemblies. And whether the assemblies repeat, I just take that same solution into this new machine. So we try and do the analysis logically and as smart as possible. But the whole point is, once I draw my machine up like this, or my process up like this, or my production plant up like this, Then I can begin saying, what loses reliability? What will cause the problems? Where does the risk come from? How do I manage that risk? And then we put those things into play. Now here's a job. And guess what? With our jobs, we have the first task and the second task and the third task. So with our jobs, we also have a series arrangement. So if I want my job to go right and I fail that task, the job can't go right. Now, the machine will go. I press the button and it'll turn. It'll work for a few days when it could have gone for a year's trouble-free. So, yeah, we can make machines work, but they should last trouble-free for their life. And if they don't, then it's because something's been amiss in possibly the repair process or the operating process. So the whole point the point here is our jobs are all series arrangements. Our machines are all series arrangements. Our production plants are all series arrangements, which means any link in the chain will fail the business. Now, whenever I bring this slide up, I always challenge people to say, are you happy with what you see there? Is there anything there in that picture that bothers you?
I see a hammer, that bothers me.
Yeah, a hammer and a roller off to one side there. So suspicion he's knocked the roller out with a hammer. These bearings, of course, are precision machines. They're precision now. They're down to sub-microns in terms of perfection. There's emery cloth. Here, they're emery cloth. I suspect he's polished the bores. Now, the interference fit isn't any more the same. And his gloves, those gloves, so that emery cloth he's used to polish and all the rubbish that came off and all the fine particles that got rubbed off by the emery are now on these gloves. So he's going to move that rubbish across all his bearings. What else do I see here? I see here air hose. I see down here bearings waiting to be used or perhaps rebuilt. Hang on, so if he blows down all this rubbish he's put on here with his gloves and it gets blown over to these bearings here, these bearings go into the machine that they're being rebuilt for, then that machine's going to fail from the wear particles that he used emery to clean the bore. I was taught to do this. This is how I was taught to maintain bearings in my trade. I was an engineer. As a maintenance manager, maintenance engineer, I would walk through countless workshops and walk straight past this. This company is failing its own machines because this practice is destroying the bearings that were going to those machines. So the company practices are leading to the company's machine failures. So companies, in my eyes, are breaking their own machinery. They're failing their own machines because if they're doing rebuild practices as this picture is showing, then it is going to naturally cause a failure. This is a process choice. Some manager in this company chose to repair bearings in this workshop in that way. It's a process choice. The process outcomes are then going to be on a distribution. That process will have a distribution. It may not be normal, it might be something else. The point is, over here is failure. And they will have failures because of those practices. May not happen every machine, but the point is the practices will create a chance of that failure to occur. Like I say, all my career, that would have been okay to me. It wasn't until I began looking to see, where are we? Page up. It wasn't until I began looking to see what makes this part reliable. How do I keep this reliable and that reliable and that reliable, that reliable? I began to look and say, you know what? That's impossible. If I adopt these practices, I cannot have high reliability in my plant because they are failing the parts that make the machine go round. Then I began to think, well, what does this mean in terms of the company and its management and its engineers and its supervision? Because this guy is just doing his job. This poor fitter is just doing his job. It's what he's taught to do by his previous trade people, and it's what he's been taught at trade school. And the engineers that go to that workshop, they don't see it either. So the engineers don't know they're destroying their own plant. The supervisor doesn't know they're destroying their own plant. The supervisor in charge of this guy doesn't know this is going to cause his machines to fail, because if he did know, he would have stopped that. Engineer doesn't know, supervisor doesn't know, manager doesn't know, And the CEO sure as heck doesn't know. And I was the same until I was 52 years old. I've been an engineer for 20 years, and I'd walk through that shop and it wouldn't bother me at all. And yet, this company destroys its own machines. And nobody in the company even sees it. So, if you go to a shop and this is what you see, then they are failing their own plant. And it means to change from this culture where it's breaking their machines to a culture where it's a clean place, proper practices, proper gloves. That's a totally different world. You know? This guy's been taught from trade school to do it this way. And his bosses have as well. And it's been wrong from the beginning. Been wrong from day one. And we've got to change that. Got to change that. Otherwise, nothing will improve. Can't improve because the process they're using causes the failure. I've got to change the process. And if that means changing a culture and changing their training and going to a different school to learn, that's what it means. And that'll affect, it's a global effect now. Better practices, more knowledge, more understanding, it's a global effect. If I train my guys to teach to look after all their bearings properly, then all the machines improve over the coming years. And so I'm going to create reliability with better practices and better techniques. That's going to come back to me as a lot of money made very easily. That's how it'll go. Yes?
I wonder what the management and the engineering department thinks is causing their machines to fail. They think something is.
Remember, a bearing's designed to be underneath that the infinite stress zone. Now, a bearing should never fail in the service life of that machine. That's how it's designed. If it's failing soon, then it's being stressed from something. Something is causing it to fail. It's not natural. Something unnatural is happening to it. Now, if they can think that way, what is causing it to fail, that's a huge step forward. If they can at least ask that question and begin looking to see for evidence, that's a huge step forward in their thinking.
I think the risk matrix has to come into play here because I believe that most CEOs and managers, vice presidents at companies accept the fact that bearings fail. They accept it. It's part of the risk that is acceptable to them.
Yeah.
They need to be shown that this is unacceptable and what the value of it is.
Yeah.
I believe that.
I think that's how I saw it too, I must admit. And to me, you've got to be a businessman. You've got to have a businessman's hat on. And that's the best way to think. You know, the engineering is great, the reliability is great, but you've got to have a business perspective, and you've got to talk to it in their language. And if we engineers can't talk business language, then we're the ones that need to lift our game. Because if we can explain things and show, well, look, this training might take a year for your crew, it might take $100,000. But after the training, you're going to win back $10 million in the coming years. It's not too hard to make a business case. So got to build a business case around the true total cost the business is actually losing and how big their risk boundary actually is. Then I can begin putting this together into a solution and say, well, you can live in this world, but it will be the same forevermore. Or we can talk about trying some different ideas, some simple techniques that are global best practice changes, and let's see what that does to your business. So yeah, we hang the carrot out, and I think a very fair carrot, a very reasonable thing to try and do. As I say, I was an engineer for 52 years old. I've been an engineer for 22 of those, and it meant nothing to me until I began looking to see why things fail and what do you do about it in particular. So yeah, this is how our tasks fail our machines. And of course the business is the same. Business has a bunch of processes that start at one end and go to the other end, and out pops the product. Your business reliability, chance of success of your business, it depends on the steps and processes in your business. So it's how our world is made. Our machines are that way, our work is that way, our companies are built in series processes. And they're high risk solutions. They are high risk outcomes because they're a chain. They're just links in a chain. I lose it there, I lose it here, I lose it there, the business suffers. Now what this is what I put on the board there. I just threw some numbers in, and I won't go through this because it's pretty much the same story. Here we have our series process, property number 1, and we talk about we want to improve our worst one first. Now that improvement in this case is 12.5%, and the system improves 12.5%. The system will never improve more than the individual improvement. Now, typically what root cause analysis does is look at a problem, solve that problem. Biggest mistake in the world. If you solve one problem on one machine and that you only fix one machine, then what you've forgotten to do is to take the global idea into your solution. Because if one machine fails, then wherever that arrangement of parts appear in any other machines, are at the same risk. So if I improve one machine's assemblies with a better strategy, then that concept, that improvement should go across every single machine, across the whole company. Then I'm not just fixing one part in one machine, I'm fixing every part in every machine that has the same arrangement of parts. Now I'm applying a global solution, I'm applying a global strategy. So if I use RCA to fix a machine, I get a small improvement. If I use RCA to fix all the machines from the learning of the RCA, now I get huge improvement from one RCA. A lot of companies don't see it that. They just fix our dog machine, get the dog working properly. Unfortunately, every other machine's at the same risk because that's the way they run their business. This one here was if we add more things to our series process, here we go. We add more components. That was just, localized reliability improvement only focuses on that local solution, which is what I was just explaining there. Here, if we add more things into our series, we have reduced the reliability of the whole series, which we've already seen. Now, property 2 is about simplification. Don't add things into your processes. Remove things, bring things together. Here's an example of the sort of stuff that it means. This particular arrangement of bearings and pillar block is what's on the end here of our head pulley. In Australia, in the mining game, thousands of these exist, and they're typically built just this way here. When you look at the assembly of our bearing, what we find there are 14 components that are used to make up this drive end here. The other way to design these things is to design them like this. In a housing, this arrangement here, 5 components. So there are 9 more ways, 9 more things to fail in this arrangement than that arrangement here. And because there are 14 things to get right here, it's very, very hard to build this thing right. To build this thing correctly is a huge challenge for a technician to do. Whereas this one here, much, much simpler. So when it says simplify, it really means that. Get from complicated stuff to simpler stuff. If you can do that, then you are removing opportunities for error. Another one here is with technology improving these days, we can put a VSD, variable speed motor, on our drive directly. So get rid of a motor here, our couplings, our shaft, and a gearbox. So I go from 5 items down to 1 item. If I can do that, I have 4 less things to go wrong. To get that shaft aligned across that distance, very hard, demanding, challenging stuff. So I've got to have chance of mistakes from human error, as well as more things to go wrong from many more parts to fail. So number 2 is about simplifying. Make your process shorter and tighter and less length. Number 3 I've discussed already. It's this story here. Bring in best practice. Bring in global change. So best practice, every machine benefits. If I introduce lubrication management, then every gearbox is going to get lubrication managed properly. It might take a number of months to go across every single machine, but in time, if I have best practice of alignment, lubrication management, interference fit control, temperature management, then that goes across every single item in the plant. So in the coming months, my best practice improvements go globally across the business. As a consequence, the system improvement is vastly more than the individual component improvement. And I have confidence this is right because these are purely the chance of success. If I increase the chance of success, then the outcome naturally follows.